Imagine a massive 10 terabyte enterprise drive failing right in the middle of your company's busiest operating hour.
Yeah, that's literally a nightmare scenario.
Right. The system starts frantically racing against the clock, trying to rebuild millions of files before a second physical drive inevitably gives out and wipes out your entire volume.
And in the real world, you can't just cross your fingers and hope the hardware holds up under that kind of pressure.
Exactly. But in the world of high-end enterprise IT architecture, surviving that kind of failure seamlessly is just, a Tuesday.
Making sure the Tuesday doesn't turn into a catastrophic outage? Well, it doesn't happen by accident. It requires a profound understanding of how data flows and how hardware actually fails.
Which brings us to why we're here. Welcome to this deep dive. If you're listening to this, you are preparing for a major professional milestone, mastering the H19-308 exam.
Consider us your study partners for this one.
Today, we aren't just going to memorize a list of acronyms or flashcards. We're going to build an enterprise storage architecture from the ground up and truly understand the logic behind the assessment criteria.
That's really the only way to tackle the H19-308 exam. It demands applied knowledge. You need to know why a specific feature was engineered the way it was.
So before we start building out our architecture, let's establish the parameters. Our sources indicate this is a written exam. You have 90 minutes to tackle 60 questions.
And those are a mix of single answer, multiple answer, and true-false, right?
Yep, exactly. And to pass, you need a score of 600 out of 1,000. There's really no room for guessing.
So what's our game plan for today?
Our strategy is simple. We are going to rigorously step through 10 actual practice questions. I will read the full question and I'll lay out all 4 options, A, B, C, and D.
And then we'll completely deconstruct both the right and the wrong answers, so you know exactly how the exam tries to trick you.
Sounds like a solid plan. We have to start at the physical bedrock. How do we ensure our enterprise storage survives when the silicon itself physically breaks?
This is all about the controller level.
Right. So here's question 1. What is the primary high availability advantage of the Smart Matrix full mesh architecture in high-end enterprise storage?
Okay, let's hear the options for this one.
Option A is, it ensures uninterrupted business operations even when multiple controllers fail simultaneously. Option B, it restricts data flow to a single dedicated path to eliminate network collisions.
Well, B is a classic exam trap right there.
Yeah, we'll get to why in a second. Option C is, it requires manual intervention to switch traffic during a hardware malfunction. And D, it disables cache mirroring to conserve power during peak performance hours.
So to understand why the correct answer is A, we have to look closely at the mechanics of a full mesh backplane.
Because legacy setups don't work like this.
Yeah, no, not at all.
Yeah.
In legacy active standby setups, controllers are often paired. If one fails, the other takes over, which is fine until both in a pair fail.
And then you're totally offline.
Exactly. But in a smart matrix full mesh architecture, every single controller is directly wired to communicate with every other controller in the cluster. It's a massive matrix of redundant pathways.
So because there's no single choke point, multiple controllers can fail simultaneously, and the surviving controllers just dynamically pick up the I/O operations.
Right. Business operations remain completely uninterrupted, which points straight to option A.
That makes perfect sense. But looking at the other options, option B almost sounds like a feature if you don't read carefully. Restricting data flow to a single dedicated path to eliminate network collisions.
Yeah. Fewer collisions sounds like a good thing on the surface.
I mean, fewer collisions sounds great, right?
It's a trap. In enterprise IT, a single dedicated path is just a dressed-up term for a single point of failure. If you restrict data to one path and a switch dies, your entire storage array goes offline.
Ah, I see. It's like routing all city traffic over one massive suspension bridge to avoid intersection crashes. Sure, no intersection crashes, but if that bridge collapses, the whole city starves.
That's a perfect analogy. High availability relies on multipathing software, where data has dozens of potential routes.
And obviously, option C, manual intervention, is the absolute enemy of high availability.
Precisely. If an administrator has to remotely log in to manually switch traffic after a controller dies, well, your applications have already timed out and crashed.
And option D, disabling cache mirroring to conserve power. That just seems reckless. If a controller dies and its write cache wasn't mirrored to another controller, you just permanently lost uncommitted data.
Yeah, you never want to sacrifice data integrity for power savings. So A is the clear winner.
All right, so we've protected the controllers, but what about the drives themselves? That brings us to question 3, which tackles block virtualization.
Well, this is a major paradigm shift in storage.
Let's read it. How does the underlying mechanism of block virtualization improve system reliability compared to traditional disk arrays?
What are they giving us for choices?
Option A. It limits data striping to a single physical drive to isolate hardware faults. Option B. It relies on a dedicated hot spare drive that remains idle until a failure occurs.
I could already see where people might get tripped up.
Yeah. Option C. It distributes data and parity blocks across all drives, allowing many drives to participate in the rebuild process. Or option D. It exclusively uses software-defined networking to bypass physical storage controllers.
The correct answer here is C. Traditional RAID ties a specific LUN to a specific physical set of drives. Block virtualization shatters that completely.
Wait, I actually have to push back here because option B sounds exactly like what we've been doing for 20 years. A dedicated hot spare drive.
Right, the old standard.
I look at option B and think, isn't a hot spare like keeping a spare tire in your trunk? Why is that suddenly the wrong answer for modern reliability?
Your spare tire analogy is exactly why traditional RAID is failing at scale. Imagine your car gets a flat tire. You swap in the spare.
Okay, simple enough.
But what if that spare tire had to, manually reinflate itself using a tiny hand pump while you were driving at highway speeds?
Oh, wow. That would be agonizing.
Exactly. In traditional arrays, if a 10-terabyte drive fails, that single, idle, hot spare drive has to sequentially write all 10 terabytes of rebuilt data by itself. It's a massive bottleneck.
So it can take days to rebuild.
Yes. And during those days, your array is degraded. If a second drive fails before it finishes, you lose the whole RAID group.
So because block virtualization scatters the data across all drives, which is option C when a drive dies, you don't have one drive struggling to rebuild.
Okay. You have 80 or 100 drives all pitching in simultaneously to rebuild the lost chunks.
That's incredible. So it slashes your rebuild penalty. What used to take days now takes minutes.
Exactly. You return to a fully protected state exponentially faster.
And obviously, option A limiting striping to a single drive is just describing a drive without any parity protection at all.
Yeah, that's just a recipe for disaster.
And option D mentions software-defined networking. As IT professionals, we know SDN is a network layer architecture. It doesn't govern how storage blocks are rebuilt on the back-end platters.
Right. Don't let the exam throw random buzzwords like SDN at you to distract from the core mechanism.
Good tip. So our hardware is bulletproof, but surviving failures isn't enough. The system has to deliver blistering performance without blowing the entire IT budget.
Speed is where things get really interesting.
Let's look at question 4, which is all about the NVMe protocol. Why is the non-volatile memory express protocol preferred over traditional storage protocols in high-performance all-flash arrays?
Let's run through those options.
Option A, it utilizes serial-attached cables to provide longer physical connection distances. Option B, it provides a massive number of concurrent queues and directly connects to the peripheral component interconnect express bus.
I mean, massive concurrent queues, that's a huge hint right there.
Totally. Option C is it relies on mechanical spinning platters to sequentially read large multimedia files. And D, it is specifically designed to operate entirely over standard Ethernet local area networks.
To get this right, you have to understand the bottleneck NVMe was invented to solve. The answer here is B. NVMe connects directly to the PCIe bus, the main high-speed nervous system of the motherboard.
So if legacy protocols like SAS are like routing all your data through a winding multi-stop local bus route, NVMe is like stepping directly onto a high-speed express subway line that goes straight to the CPU.
That's a great way to visualize it. But the second half of option B is just as critical, the concurrent queues.
How many queues are we talking about?
Well, legacy SAS protocols basically have one queue that can hold about 254 commands. NVMe supports up to 64,000 queues.
Wait, really? 64,000?
Yeah, and each of those queues can hold 64,000 commands. It perfectly matches the massive parallelism of modern flash memory.
Which tells us exactly why option A is incorrect. SAS serial-attached SCSI relies on those older serial cables, which just can't deliver that parallel throughput.
Right, and option C mentions mechanical spinning platters, which is describing legacy hard disk drives. The question specifically referenced all flash arrays.
Now I want to ask about option D. It says it's designed to operate entirely over standard Ethernet LANs. Now, NVMe over Fabric's NVMe does exist, and it can run over Ethernet, so why is D the wrong answer here?
That is a brilliant distinction, and it's exactly the kind of nuance the H19-308 exam tests.
So it's a distractor.
Totally. NVMe over fabrics extends the protocol across the network, yes. But the core NVMe protocol itself, the reason it's fundamentally preferred over legacy protocols, is its direct PCI architecture inside the array.
Ah, I see. Option D implies NVMe was specifically designed to just be an Ethernet protocol, which misrepresents its foundational advantage.
Exactly. You have to identify the primary architectural differentiator.
Got it. Now, speaking of optimizing our arrays, we have all this incredible NVMe flash, but it is expensive. How do we manage the economics of that speed?
Cost control is huge. You can't just buy flash for everything.
Let's read question 10 on automated storage tiering. How does an automated storage tiering feature optimize both performance and cost within a hybrid storage array?
Let's hear the choices.
Option A. It permanently pins all newly created volumes to the solid-state drive tier regardless of access frequency.
Well, that sounds incredibly expensive.
Doesn't it?
Yeah.
Option B. It dynamically moves frequently accessed data to high-performance media and inactive data to high-capacity media. Option C. It creates a complete replica of the primary volume onto a secondary array during off-peak hours.
And was the last one?
Option D, it compresses all data equally before writing it to a single homogeneous storage pool.
The mechanism of automated tiering really hinges on telemetry. The correct answer is B. The storage controller constantly analyzes access patterns.
Tracking hot and cold data, right.
Exactly. It tracks hot data, like the databases getting hammered with I/O, and cold data, like last year's log files. It dynamically promotes the hot blocks to the expensive NVMe flash and demotes the cold blocks down to cheap hard drives.
I'll admit, option A sounds tempting at first glance. If I want maximum performance, shouldn't I just pin everything to the solid-state tier right when it's created?
You could, but you really would bankrupt your IT department. If you permanently pin everything to flash, you rapidly fill up your most expensive media with cold, inactive data.
Which completely destroys the ROI of purchasing a hybrid array in the first place.
Right. The entire point of tiering is dynamic, intelligent movement based on actual workload demands.
That makes sense.
Yeah.
And option C describes a replication or backup process, not tiering.
Yep.
And option D mentions a single homogeneous storage pool, which literally means removing the tiers entirely. You can't have tiering in a homogeneous pool.
Spot on. The exam is testing your ability to distinguish between distinct storage services.
Okay, so we have a fast, efficient, highly available block storage system. But the reality of modern enterprise IT is that structured block data is only a fraction of the footprint.
Yeah, unstructured data is growing exponentially.
Cloud-native apps, massive media libraries, IoT telemetry, traditional file systems just hit a wall at that scale. That brings us to question 6, focusing on object storage.
Traditional file systems really struggle here.
What architectural characteristic makes object storage highly scalable for cloud-native applications compared to traditional file storage? Option A, it utilizes a deep hierarchical folder structure that mimics a traditional filing cabinet.
But we know that's not scalable.
Right. Option B, it maps storage resources directly to the host operating system as raw physical volumes. Option C, it requires synchronous mirroring across all local network nodes before confirming a write operation.
And the correct option.
Option D, it eliminates folder hierarchies in favor of a flat namespace utilizing unique identifiers and metadata.
D is the winner. This is a core competency for the H19-308 exam. Traditional NAS uses a massive tree of directories and subdirectories.
Oh, like a labyrinth.
Exactly. As you get into the billions of files, the system spends more compute power just traversing the directory tree than it does serving the files. Object storage completely flattens the namespace.
I always think of traditional NAS file storage like a massive library. You have to know the floor, the aisle, the specific shelf, and the binder just to find a single document.
It's exhausting just thinking about it.
But object storage is like a magical valet parking service. You hand the valet your data, and they give you a unique ticket, the unique ID and rich metadata.
That valet analogy perfectly captures the mechanism. You don't care where the valet parked it when you want it back. You just hand the system your unique ticket, and it retrieves it instantly.
Whether the garage holds 100 items or 100 billion.
Right, because the system isn't maintaining a fragile interlinked directory tree. You can just keep adding storage nodes horizontally.
Right.
The flat namespace scales almost infinitely.
Which explains why option A is dead wrong. Deep folder hierarchies are the exact bottleneck we are trying to escape.
And option B describes mapping raw physical volumes, which is the definition of SAN block storage, not object storage.
And option C, synchronous mirroring, is a data protection policy. It has nothing to do with the namespace architecture itself.
Right. And one of the biggest advantages of that object metadata is how we can interact with it across different protocols.
Which leads perfectly into the complexities of data access. Let's look at question 5, which deals with multi-protocol interworking.
This is a huge architectural leap forward.
What is the primary benefit of the multi-protocol interworking capability in distributed storage systems for unstructured data? Option A, it automatically converts high-definition video into basic text formats for faster transmission.
Okay, that sounds like something from a sci-fi movie.
Yeah, quite the feature. Option B, it restricts file access to a single proprietary protocol to maximize security. Option C, it requires data to be copied into separate isolated storage pools for different applications.
And option D.
Option D, it allows the same set of data to be accessed via file, object, and big data interfaces without data migration.
The answer is D. Historically, if a media ingest application wrote data via a file protocol like NFS, and your data science team wanted to run Hadoop analytics on that data.
You had to physically copy all that data to a separate Hadoop cluster, right?
Yes. It took days, and it wasted massive amounts of capacity, which is exactly what option C describes, copying data to isolated pools.
That creates data silos, which is the exact headache multi-protocol interworking was engineered to solve.
Precisely. With true multi-protocol interworking, the underlying storage system translates the access protocols on the fly. Zero copying, zero migration.
I love how option A tries to trick you here. Automatically converting video to text. That sounds like a cool feature, but that's an application layer AI task.
Spot on. The storage protocol layer doesn't transcribe video. You have to isolate what the storage layer is actually responsible for.
Okay, so we've built a system that is incredibly resilient, fast, auto-tiering, and infinitely scalable without creating data silos. But what happens when the entire physical data center loses power?
Or a natural disaster wipes out the local grid.
Exactly. We need to talk about disaster recovery metrics. Let's look at question 9. During a disaster recovery planning session, the Chief Information Officer states that the company cannot tolerate losing more than 15 minutes of transaction data. Which metric does this requirement define?
This is a fundamental concept, and the exam will definitely test your ability to differentiate these terms.
Option A is recovery time objective. Option B, maximum tolerable downtime. Option C, service level agreement availability. Or option D, recovery point objective.
The answer is D, recovery point objective, or RPO.
I know a lot of people see 15 minutes and immediately jump to option A, recovery time objective. Why is RTO the wrong answer here?
Think of a timeline. The moment disaster strikes is your 0 point. RPO looks backwards in time. It measures data loss.
So if your last backup was taken 15 minutes ago, your RPO is 15 minutes.
Exactly. That's the transaction data you permanently lost. RTO, on the other hand, looks forwards in time. It measures downtime.
The amount of time it takes your IT team to get the replacement servers online and restored.
Right. The CIO in this question specifically limited transaction data loss, not system downtime. Therefore, it's RPO.
That distinction is crucial. Now, what if the CIO says, I don't want to lose 15 minutes. I want to lose 0 minutes. How do we architect that?
That's where things get expensive, but very impressive.
That brings us to question 2. Which statement accurately describes the recovery capabilities of the active storage feature?
Active is the gold standard. What are the choices?
Option A, it achieves a recovery point objective of 0 and a recovery time objective close to 0. Option B, it focuses primarily on asynchronous replication for distant geographical sites.
Those are very different approaches.
Yep. Option C, it guarantees a recovery time objective of exactly 24 hours for archived data. And option D, it utilizes a scheduled snapshot mechanism to ensure data consistency every hour.
If you understood the RPO and RTO distinction, option A is the only logical answer here.
Because in an active architecture, you have 2 separate data centers synchronously mirroring every single write operation in real time.
Exactly. The host doesn't receive a write acknowledgement until both Site A and Site B have committed the data.
So because they are synchronized in real time, if Site A burns to the ground, Site B already has the exact same data. You lose 0 data, meaning your RPO is 0.
Yeah, because Site B's infrastructure is already actively serving applications, failover is almost instant, making your RTO near 0.
But there's a catch that explains why option B is wrong, right? Option B mentions asynchronous replication for distant geographical sites.
Yes. Active requires synchronous replication, which is severely limited by the speed of light. If the data centers are too far apart, the latency of waiting for both sites to commit the write will paralyze your applications.
So active is usually limited to a metro area distance.
Right. Asynchronous replication is used for long distances, but because it batches data and sends it on a delay, whatever data was in transit during a disaster is lost.
So an asynchronous setup cannot guarantee an RPO of 0. That's a brilliant architectural insight.
And obviously, option D, utilizing an hourly snapshot, is an RPO of 1 hour. If the system crashes at minute 59, you lose 59 minutes of data. It's definitely not active-active.
Now, achieving all this requires massive amounts of backup data. Let's look at question 7. Which feature is critical for a dedicated backup storage system to minimize the required physical capacity for storing multiple backup copies?
Let's see the options for minimizing capacity.
Option A, continuous synchronous replication to a secondary site. Option B, variable length data deduplication and intelligent compression algorithms.
I think we have a winner with B.
Let's read the rest, just in case. Option C, unrestricted multi-tenant access control for public cloud integration. And option D, bypassing cache to write data directly to secondary optical media.
Definitely B add. When you are dealing with backups, you are storing the same operating systems and the same databases over and over again. Deduplication scans the incoming data streams, finds identical blocks of data, and stores only one unique instance.
And it replaces all the duplicates with tiny metadata pointers, right?
Exactly.
And variable length deduplication is key here because instead of just chopping the data into rigid, fixed blocks, the algorithm uses a sliding window to find duplicate patterns even if the file has been slightly modified.
Right. Variable length yields a vastly higher data reduction ratio for backups. Add mathematical compression on top of that, and you can logically store hundreds of terabytes of backup data on a fraction of the physical disk space.
Which is the exact opposite of option A. Replication makes one-to-one copies of your data. It doubles your required physical capacity. It doesn't minimize it.
And option D, writing to optical media, is just changing the physical medium. It doesn't mathematically reduce the data footprint. Moving a heavy box from the floor to a table doesn't make the box any lighter.
I love that. Okay, we are at the final piece of the architecture puzzle. We've protected data from hardware failure and natural disasters, but the greatest threat to data is often internal.
Oh, absolutely. People are the biggest variable.
How do we protect data from malicious actors or accidental deletion, especially in highly regulated industries? Let's look at question 8. In a healthcare scenario requiring strict data compliance, how does the write once read many feature protect electronic medical records?
Write once read many, or worm. Let's hear the options.
Option A, it encrypts the records during transit between the hospital branch and the main data center. Option B, it automatically deletes the oldest records to ensure sufficient space for new patients.
Wow, B is a massive compliance violation right out of the gate.
Yeah, that would be bad. Option C, it prevents any modification or deletion of the data for a specified retention period. And option D, it grants full administrative privileges to the primary attending physician only.
The correct answer is C. Worm is the ultimate digital padlock. At the storage layer, once a file is committed to a worm state, a clock starts.
And until that retention period expires, which could be 7 years for financial data or the lifetime of a patient for healthcare, absolutely no one can alter or delete that file.
It ensures total, unassailable auditability.
I want to ask about option D, granting full administrative privileges to the attending physician. Let's say the chief medical officer and the IT systems admin both agree a file needs to be deleted. Can't they override the worm lock?
No. That is the entire point of worm compliance. If an administrator could override it, a hacker who steals those admin credentials could execute a ransomware attack and delete the backups.
Oh, wow. So true worm compliance protects the data from everyone, regardless of their privilege level. That is fascinating. And what about option A? Encryption is critical for compliance. Why is it the wrong answer here?
Option A specifically describes encryption in transit. That protects the data from eavesdroppers while it moves across the network. But once the data lands on the storage array, if it isn't locked down by worm, an authorized user could still log in, open the file, alter the medical record, and save it.
Ah, so encryption doesn't provide immutability, only worm does.
Exactly.
Well, there you have it. Thank you for joining us on this deep dive. Go crush the H19-308 exam.